Hello! I want to take a quick look at some of the signals going into and out of a flight controller. In this case, a Nausea 32. So the setup I've got right here is a simple RC receiver going into the Nausea 32 via PWM, so I've got individual connections per channel. Right now I've got channel 3 being probed, and that's what we're seeing up on the screen. On the outputs, I currently have motor 1 set up on the second probe. So again, the key point of interest here is I want to see what the frequency of the signal is coming into the flight controller and then going out to the motor, because there's a lot of common terms as far as looking at a receiver refresh rate as being something like 50 Hertz, and oftentimes you'll see motors and ESCs rated, or excuse me, ESCs and motor outputs rated at about 400 Hertz. So I wanted to take a look at those and see what those actually look like on the screen. Over here I've got a 16-volt power supply that is switchable, feeding an ESC, and then the ESC's signal wire is where I'm getting the 5 volts to power the Nausea 32 and the receiver. So let me go ahead and power that up. And you can see, again, looking at input channel 3, which in this case is the throttle input. If I grab the transmitter and start moving that, you can see over here on the screen we have a variation between 1 millisecond and 2 milliseconds. And this is what we'd expect if you've looked at, make sure things aren't spilling. Anyhow, the settings in something like the multi or baseflight configurator, looking at the raw values, you'll see things in terms of 1000 to 2000 with maybe 1500 as a midpoint. So if I run the throttle here, let's say halfway, you can see we've got 1 and then half of a division, which we're currently looking at camera overheating. Allow it to cool. Where 1 millisecond represents 0 and 2 milliseconds represents 100%. And as I move the throttle up and down on the transmitter, you can see that's exactly what we're getting. Looking over at the settings here, we've got a 1 millisecond division. So we can see with the throttle all the way down, we're seeing a period, or excuse me, a time of 1 millisecond. Full throttle gives 2 milliseconds. So that is giving our 0 to 100%. One thing you'll notice that's interesting about this is that's only taking up a very small part of the waveform. And as a matter of fact, I don't know if we can see just past this edge. I might need to switch this down a bit. Yes, even if I go down to 2 milliseconds of division, you can see we're only just seeing the next signal coming in. So we've got a ton of dead time in between here. And this is simply due to the update rate of the receiver itself. We're only looking at a single channel split off of this, and in this case there's 7 more for a total of 8. So if I bring this down even more, we can see the display's quite flickery now, but we can see the repeat. However, this would give a good measurement. We're currently looking at 5 milliseconds of division, and if we count through here we have 5, 10, 15, 20 milliseconds. So we have a 20 millisecond period on this incoming signal, and that gives us a refresh rate of 50 Hertz. So that's where the 50 Hertz comes in. Again, to further explain the reason we have so much dead time in here, we have to share this entire space with 8 channels. So we're using a small part here, but now imagine the rest of the channels throughout here. As a matter of fact, if you were running CPPM with all 8 channels on one wire, then we'd actually be able to see all of the channels at once. But in this case I happen to be running just normal PWM on each channel. So even though, and what's interesting is even though that's termed PWM for pulse width modulation, it's not exactly normal pulse width modulation in the sense that it's one channel but compressed into the smaller time envelope. So if you were looking at a quote-unquote normal PWM, this entire time you'd see 0 being represented by a very small, very short pulse width here, and then 100% being nearly or all the way across to the next period. So that's interesting. It's termed PWM, but it's like it's using a fraction of the PWM space. Alright, so we've seen the data that's coming into the flight controller. I'm going to go ahead and arm the flight controller now, so we should be getting information out on the output pin. I mean, technically we were even before arming. But I'm also going to switch over to channel 2 on the scope. That's not channel 2, that is. And look at that. With the flight controller armed, if I raise the throttle now, you'll hear the motor start up and you'll see the waveform start to change. But before we look at going throughout the throttle range, the first thing of interest is how much faster this signal is. we've got the scope set to where we were seeing an entire 20 millisecond period for the incoming waveform. In this case, we have a much faster signal. To get an idea of how much faster, let me switch the scope over to half a millisecond per division, and then count up, or roughly count up, the period of this waveform. So we've got 0.5, 1, 1.5, 2, 2.5-ish. And 2.5 milliseconds correlates to 400 hertz. So there is our 400 hertz input. Again, that you might see on an ESC as being rated as supporting high rate input or fast input. And that meaning of like, okay, it supports up to 400 or a little over 400 hertz. That's what it's meaning. It will accept a signal with a period of, say, 2.5 milliseconds. And the reason we want this on a multirotor, of course, is that way faster update rate means that we get the information to the ESC as fast as humanly possible. Now let's go ahead and spin the motor up, and you'll notice that there's, between the motor cutting in and out there, you can see that there was a little bit of a jump. And what that is simply a minimum throttle configured. So that way we're not worrying about getting the motor as low as it can go. We want there to be some threshold because we don't want individual motors cutting in and out at low throttle. Now if I run through the throttle range, you'll notice that we still have a little bit of a pillow up here. This pulse doesn't make it all the way across. The motors are not configured to go to a full 100% throttle off the flight controller, just to reserve some headroom for maneuvering at full throttle. But anyhow, that's a quick look at the input signal versus output signal and the related timing. As a matter of fact, to get, once again, a good idea of the difference here, let me jump down to, I think it's 2 milliseconds division. Go back to our input signal. So once again, you can see the relative speed difference, rather frequency difference between the incoming signal at 50 hertz to the output signal of about 400 hertz. Now, one other interesting thing is I currently have it set up in tricopter mode. So the first two outputs are configured as servo outputs. And one of the considerations there is the fact that servos generally run at the same 50 hertz refresh rate that receivers do. So to take a quick look at that, I'm going to power down the setup briefly here so I can safely swap this over. So I'm going to take my probe, channel 2, and move that over to pin 1 on the Nausea 32. Let me go ahead and power the system back up. And you can see that once again we have a 50 hertz or thereabouts refresh rate. So we can zoom up on that a little bit and see that in this case, so all the way, yawing all the way to the left gives us a period of about 1 millisecond, all the way to the right gives us 2 milliseconds. So this also makes sense in terms of the fact that servos are usually plugged directly into receivers. So it would make sense that all the signals line up. And also the fact that 400 hertz output is also something that's, I guess you could say, comparatively new, more or less targeted at multirotors. Since prior to multirotors, 50 hertz update rate as a primary control and being fed to servos was, fine for speed and control. And it's with the advent of wanting to have really, really tight control over motors that that things have been cranked up to 400 hertz. But again, I just wanted to give a quick look at that, show the input and output going into the system, and actually look at the fact that yes, we're getting 400 hertz out on the motor outputs, but in this case we have the servo output still at the default 50 hertz that would be coming in from a transmitter.